yeah, where do we begin? This actually is the last slide in part 7. Okay. And I have queued up to go part 7, 8, and 9. Bless you. So, let's see. So, actually, this is the, what was this, the last slide? Right before this one we were doing, oh yeah. Okay, we did an example of, maybe this wasn't yours. Okay, but these are Lewis structure related problems that are due on Monday. So let's take a quick look at these and see what sort of hints, if any, we got going on. This one right here. Okay. So I don't have hints per se, like written out, but so for instance 9, what's wrong with these 2 Lewis structures? Now for all of these, kind of what's wrong with the Lewis structure, that sort of thing. One of the things I would suggest is to come up with a pot of electrons. Come back here. That was me, that was not technology. I would come up with a pot of electrons and see if the right number are distributed around them. Okay, so that's my first hint. Pot of valence electrons, just like you did step 1 yesterday. The other thing, though, actually I can tell you right off the bat, one of the things that looks funky, I'm not doing your homework for you, but doesn't that look weird, hydrogen in the middle like that? You know, hydrogen only wants to reach out once. That is pretty strange to me. And I had a student come by today, and actually the thing that looks wrong about this, that is wrong about this one, it may not be very obvious, but since calcium is a metal, okay, that really should be an ionic compound, yeah. And the way, let's see if there's an example here. Down here, this is the way Petrucci shows ionic compounds. So basically down here, and this is weird too, isn't it? This actually falls under the category of indicate what's wrong with each of these. Chlorine and oxygen are both nonmetals, so you figure electrons should be shared. They're actually, if you look at it a few times, showing valence electrons being transferred from the chlorine atom. You're like, chlorine doesn't want to do that. Okay, so that does not make sense. But my point up here again is they are actually showing electrons being shared. Electrons shared? I don't think so. Okay, probably it should be shown like the other one down there is, where it's just calcium a +2 and oxygen a -2 next to each other. So let's see, I don't have a lot of hints about that. My hint was come up with a pot of valence electrons, and or just find out what you think doesn't look right about those. Let's see, it's almost easier to draw them yourself. Next page. Okay, 25. Say, now I do have a few hints here. And I didn't realize this till today, Maria came by, my 25 answer key does not match up with this 25 answer key. But I can show you what you might find helpful is when you draw the Lewis structure, for instance, of that thing, basically I'm just going to show you kind of the, it's going to have the 2 nitrogens are going to be together, and it's going to have 2 hydrogens kicking off of that. Now that's not the finished Lewis structure, okay? And on Lewis structures on your test, you will have 1 atom in the middle and stuff breaking out of that. For the next one, I think this would be for B. I think actually the order of the atoms is right. So the chlorine is in the middle. It's singly bonded to, or not singly bonded, the chlorine, not the carbon. The chlorine is bonded to 2 oxygens, and one of those oxygens is also bonded to a hydrogen. So why don't you go see what you can do with that one for B. For C, we have a sulfur in the middle. I wish I had looked at my answer key. For C, we have a sulfur in the middle, and it's singly bonded to an oxygen, and then it's also singly bonded to 2 OH groups. See what you can do with that one. For the hydrogen peroxide, the H2O2, that's correct just as it is. Single bond, Okay. For D, it is HOOH. Again, not the final Lewis structure. And E should look pretty familiar because you guys did it. Okay, in lab yesterday. Number 26, I'm just going to kind of see what you can do with that. See what you can do, kind of finding how those 4 atoms might fit together to make 2 different isomers. 27, I think you should be fine. Propose an acceptable Lewis structure for each. Those look like what you did in lab yesterday. Now for 28, my suggestion for 28 is to kind of do what we did in lab 2 weeks ago. Okay, first, so barium hydroxide, it's an ionic compound. What I would do is write the component ions. So barium, it's a 2A, so I'd write +2. Hydroxide is one of those polyatomic ions you're supposed to commit to memory. So actually the formula for that thing is, looks like we need only 1 barium and we need 2 hydroxide groups. Okay, so I would start with that. And then what I would do is, again, I'm not you, but I would draw the Lewis structure for the polyatomic ions. Lewis structure for polyatomic ions. Okay, so what's the Lewis structure for OH minus? Okay, and then actually I would connect it to my Ba plus in the middle. So you have polyatomic ions here of nitrate, iodate, and sulfate. So that's your hints for that one. So that's due on Monday. Okay, sometimes the homework, it frustrates me. That's okay. Okay, so the next part, that was 7. Now for part 8, we're actually going to go ahead and do a few slides. Clear at the front of part 8. And I think I hid the slides when I get to the part that we've done. We still need to talk about bond properties. This should work just fine. Oh man, and I printed out, it's on the printer. I printed out these complete slides for you, so the blanks that we didn't fill in Wednesday, I actually have the hard copy for you, which I guess I'll give to you on Monday. Okay, bond properties. So a triple bond is the strongest of all bonds. Remember, triple bond is 1 sigma, 2 pi. Double bond is a little bit weaker, and a single bond is even weaker than that. Like this says, if you have like a triple bond, the pi bond is the weakest. The sigma bond is stronger than the pi bond between the same 2 atoms. So we kind of have this sort of situation. If you're talking about bond energy, triple bond stronger than single bond. Okay. Again, you have to make sure that you're comparing apples to apples. So in all of these cases, the same pair of atoms are joined together. So this actually is some energies associated with the bonds. This would be the amount of energy released as the bond is formed and the amount of energy required to kill the bond. Okay. Very good. So bond length, and I kind of mentioned this yesterday. Your triple bond actually is the shortest option as long as you're comparing the same 2 atoms. Your double bond is shorter than a single bond. Now, if you have the same type of bond, that being single, double, or triple, as the size of the atom increases, so also does the bond length. And we talked about atomic size earlier. Okay, so that ends up looking something like this. Okay, so with regard to, it's short for the triple bond, it's longer for the single bond. Okay, short for the triple bond, longer for the single bond. Again, comparing apples to apples. So these last ones, no, not these. Okay, I think you should be fine there. Okay. Now, that was it for bond properties, and then we went into orbital hybridization. Now, I just randomly picked a few of the last slides. This slide emphasizes The types of orbital hybridization in lab, we talked about these types of orbital hybridization where you have 2, 3, and 4 electron domains that are participating in either sigma bonds or lone pair electrons. These are the expanded valences, okay, where actually in the sp3d you're looking at actually 10 electrons around that atom. sp3d2 you're looking at 12 electrons around that atom. So in the homework that's due for this part, that's what you're looking for to know if you have an expanded valence or not, I think. I guess put another way, or put more appropriately, this is sp3d, and this is sp3d2. So if you have, what, 5 electron domains occupied with either sigma bonds or lone pair electrons, that's what it's going to look like, the trigonal bipyramidal. If you have, what, 6 things, either sigma bonds or lone pair electrons around an atom, then that actually is the geometry we call octahedral, sp3d2. There we go, the balloons. Hard to go wrong with balloons. So then skipping ahead, I thought we'd take one more look at kind of what we did in lab. Actually, we did this one. The nitrogen has 3 sigma bonds and 1 lone pair electron, so we're looking at 4. So you're looking at sp3 orbital hybridization. Okay. Formaldehyde, again, we have to, in order to talk about some sort of structural geometry, we need to say what atom we're looking at. So in this case, follow the arrow, that oxygen atom. We have, looks like the carbon atom. So the carbon atom here, we have 3 sigma bonds, no lone pair electrons. So we're looking at sp2 orbital hybridizations, trigonal planar, 120 degrees. For that chlorine atom, looks like we have 3 lone pair electrons, 1 sigma bond, sp3 orbital hybridization. No bond angle, right? Okay. And we did this. Okay. We did a couple of them anyway. I'll just go ahead and fill all these in case you want to fill them in your notes. So I think we did the carbon is sp3 orbital hybridization. The geometry is tetrahedral. That oxygen has 1 sigma bond, 2 lone pair electrons. It's sp2 orbital hybridized. This carbon atom over here, I don't think we did. It actually has 3 sigma bonds, no lone pair electrons, so it's sp2 orbital hybridized. Then this nitrogen atom has 1 sigma bond, 1 lone pair electron, so it's sp orbital hybridized linear. I think we did that bond. The first bond angle is 109.5. Okay, the second bond angle, to me, you can only get a bond angle after you figure out what its orbital hybridization is. So it has 3 sigma bonds, no lone pair electrons. So it's sp2 orbital hybridized, trigonal planar, so it's bond angle of 120. Around that carbon atom, we have 2 sigma bonds, no lone pair electrons, so it must be sp orbital hybridized, so you're looking at linear. So the bond angle's 180. Okay. All right, so skipping to the assignment slide there. Looks like this. I'll pull up some hints, hopefully. $11.7 must look like this. Okay, so and I don't say it on here, but I think I will go ahead and say it. My hint, come back here, is to basically draw the Lewis structure and say what the orbital hybridization is around the central atom. I know it says something about what is the hybridization scheme, but just tell me what the orbital hybridization is. So draw Lewis structure. I miss my stylus. Okay, and then say what is orbital hybridization. Ugh. Thank goodness it's Friday. So you should be fine with a carbon dioxide molecule. The HONO2, I went ahead and drew it out for you, what it looks like. Now that's not the final Lewis structure. And then say what the hybridization of the nitrogen atom is. For the ClO3, the chlorine's in the middle, 3 oxygens coming out. The BF4, those are both polyatomic anions. Borons in the middle, 4 fluorines coming out. And you should be fine with 8 also. Draw the nitrogen, sulfur, and fluorine, what that Lewis structure would look like. All right. This one. Okay, yeah, actually on the slides it told you that these actually have expanded valences. So that's the only hint you really didn't need me to say because it's already on the slide. So the central atoms, the chlorine in the first place and the sulfur in the second place, have expanded valences. When you come up with the pot of valence electrons, actually you're going to see that they have more than 8 around them. So, and then the next one, draw the Lewis structure and describe the hybridization of the central or internal atom or atoms. All right, so I went ahead and for methyl alcohol broke it out and kind of showed you the rough structure. It's not the final Lewis structure. And for acetone, this is kind of the rough structure of acetone. That's the rough structure of carbamic acid. That should work. Well, wait, there's more. Okay. So draw the Lewis structure and then consider kind of how the geometry is around each atom. So I'll kind of show you, for example, I'm not focusing as much on the shape of the molecule like question 13. I am focusing more on the electron pair geometry comes from the hybridization around a particular atom. But if we look at A, we have, that actually is it's not the final Lewis structure, but you do definitely have carbon doubly bonded to carbon, singly bonded to the chlorine atoms here. So the hybridization around those carbon atoms are sp2, and so that's trigonal planar. So actually the way this works out is A actually ends up being planar. The whole molecule is planar because the carbon, as the carbons reach out to each other and to the chlorine atoms, those are all planar. If we compare that to C, actually here we have a carbon that has 4 sigma bonds around it. 4 sigma bonds means sp3 orbital hybridization. That thing is tetrahedral, so that thing definitely fluffs out of a plane. It's not contained in a plane, so that is not planar. So that's kind of how you take a Lewis structure and kind of fluff it out into what would the shape of the molecule be. And I think that's it. All right. On to, that was 8. On to, so that will also be due on Monday. On to 9. Now, I don't know if we'll get all the way through formal charges. We might. If we do, just because I don't think I want to grade all that over Thanksgiving, I'm thinking about not having the homework assigned. Okay. Oops. So it looks like we're all keeping up okay, kind of picking up some loose ends. I think the only loose end that I have, well, I have 2 loose ends earlier. I have some slides at the end of part 6 that we didn't do for polyatomic ions. I don't know if we're going to necessarily might do those for review, but at the end of part 5, I still have ionization energy and electron affinity. But this is the end of part 9. This is the last part before we get to unit 5. So, formal charges, right. So formal charges are kind of faux sort of charges. They're the apparent charge on an atom as it exists in a molecule, as you basically push that atom to be, push that atom to what we call the nonpolar limit, okay? So remember we said that polarity actually comes, well, remember we said that atoms can share electrons, but if they aren't shared equally, we get a degree of polarity, okay? And actually that comes from the electronegativity difference. So we're going to assume that basically electrons are going to be entirely shared equally in covalent bonds, which is not true. We're basically going to throw their electronegativity out the door. So at this little sort of, on our final Lewis structure, wherever you see a pair of electrons that are being shared, we are going to assume that they're shared equally, and we're going to divvy them up. It's kind of like a fun little game. Okay, and it's, again, it's not the way it really is. It's kind of faux, but now if an atom has lone pair electrons, okay, then those lone pair electrons will go with the atom. Okay, so the lone pair electrons stay with the atom. If there's a sigma bond or a pi bond, for each bond, they split the electrons equally. Then the way you calculate the formal charge is a little subtraction problem. Okay, you go to the periodic table, so this first number comes from the periodic table, and you look at the periodic table, you find the number of valence electrons for an atom of that type. And then from that, you subtract the number of electrons that you came up with when you divvied up the electrons from the Lewis structure, okay, assuming the nonpolar limit. Okay, and it's easier to show you than to explain, okay? So again, how do we come up with this number here? We use the Lewis structure, okay? And again, each atom retains possession of its lone pairs, and for every atom that is singly bonded or doubly bonded or triply bonded, for every one bond, it gets one electron. So I'll kind of show you what that looks like. So actually, this idea of looking at the formal charges of all the atoms in your Lewis structure is a way to see how solid your Lewis structure is. If it's a good solid Lewis structure, good chance that all of your atoms have a formal charge of 0. It's kind of weird. I guess it's not kind of weird. It's kind of the way it should be. So the closer to 0, the closer to having a formal charge of 0 all atoms are, the more stable that particular Lewis structure. If you do have kind of a negative formal charge and a positive formal charge, the negative formal charges should tend to be on the nonmetals, okay, and the positive formal charges should tend to be on the metals, or at least kind of divided that way with regard to electronegativity. Once you assign formal charges for all of the atoms, if it's a neutral molecule, then if you do have some positive and negative formal charges, they should actually cancel each other too. Should be neutral. If you are dealing with a Lewis structure of a polyatomic ion, the sum of the charge of all of your formal charges should actually be equal to the charge on your overall polyatomic ion. Seems reasonable. Okay, so again, this idea of assigning formal charges to atoms in a Lewis structure of a molecule or polyatomic ion, it's a little bit faux, okay? But they do, one of the things that they help you do, in addition to seeing if you have the best Lewis structure possible, is they help you to know where the partial negativity and partial positiveness of a molecule would be. So I'm going to do one example. So we need to assign a formal charge to the hydrogen, the 3 oxygens, and the 1 nitrogen. Okay, so again, the first number when we do the subtraction here in a minute to come up with the formal charge is going to be the number of valence electrons of hydrogen. It looks like it's 1 valence electron. Valence electrons for an oxygen, since it's 6A, is 6 valence electrons. Nitrogen's 5A, 5 valence electrons, okay? So, but we need to divvy up the electrons at the nonpolar limit, and this is what it looks like. So up there you have the original Lewis structure. Down here, kind of with these little Venn diagram sort of things, you basically have the electrons divvied up at the nonpolar limit. So for instance, in this case, you think of splitting those pair of electrons. So 1 electron went here, 1 electron went here. With regard to this oxygen atom, notice it had 2 lone pair electrons coming along for the ride. It also picked up another electron from its single bond with the nitrogen. So that's kind of how that works. It's kind of fun. Over here, when it came time for this double bond right here, okay, notice that 2 of those 4 electrons went with nitrogen, 2 went with oxygen. Okay, so that second number that we're going to subtract from their valence electrons is going to be 1, okay? It's going to be 6 here, it's going to be 7 here, it's going to be 4 here, and it's going to be 6 here. Okay, that is the number of electrons at the nonpolar limit. Oops, yeah. So the next slide actually goes ahead and comes up with the formal charges. Okay, so again, formal charge is the number of valence electrons for hydrogen is 1. The number of electrons at the nonpolar limit is also 1 for this particular Lewis structure. So it's 0, which is good. That's kind of what you're after. For this oxygen, oxygen has 6 valence electrons. In this particular situation, at the nonpolar limit, we've got 6 electrons. Looking pretty good. Again, same thing over here. We have a formal charge of 0. So that must be something funky is going to go on with the nitrogen and the oxygen, or I wouldn't have picked this as an example, and it is. So notice up here with this oxygen, oxygen 6A, it has 6 valence electrons. In this particular case, actually at the nonpolar limit, it's actually got 7 electrons. So its formal charge is -1. This nitrogen atom, it's 5A, it's got 5 valence electrons. In this case, it's got 4 electrons at the nonpolar limit, so it's actually got a formal charge of +1. Again, one of the rules of formal charges is that if it's a neutral molecule like this is, the formal charges should be equal to 0, and they are if you sum them together. But what we can say is that with regard to region of positiveness, with regard to the polarity of the molecule, because this is a formal charge of +1, this is a general region of partial positiveness, and the oxygen's -1 region of partial negativeness. So let's take one more look at that carbon dioxide that we looked at earlier in part 9. So you guys would probably tell me that this structure makes more sense, and it does. And we said for one reason, actually, oxygen expected valence is 2, because you take 8 minus the group number. 8 minus 6 is 2, and it's only reaching out once there, so that just does not make sense. But if we go ahead and assign formal charges to the atoms, let's see what that looks like. Okay, so these are how the electrons would be distributed at the nonpolar limit for that kind of looking, the one that looked normal. So if we were to come up with the formal charge, okay, remember it's the number of valence electrons. So for this oxygen, it's, well, each oxygen, valence electrons are 6, okay, -6, okay, is equal to 0. That's the same thing for both oxygen atoms. Carbon, it's 4A, so it has 4 valence electrons, -4 electrons there. Okay, it's also 0. So that one's cool. But if we go over here, okay, to where we had the oxygen, single bond carbon, triple bond oxygen, okay, notice when we go to divvy up the electrons at the nonpolar limit, that first oxygen, okay, ends up with, of course, it had possession of those lone pair electrons, and it gets possession of that one because it's a single bond there. So actually, we take the valence electrons, which is the group number 6, minus the number of electrons at the nonpolar limit, which, so it's 7. So we get a -1 for that oxygen. Let's look at the other oxygen. Okay, again, we take 6 valence electrons minus, it's looking like 5 there. So we get a +1 for that oxygen. It's looking like carbon's going to be 0, though, because carbon is got 4 valence electrons minus 4 electrons here at the nonpolar limit. Okay, but just this idea that you have separation of formal charges when you wouldn't necessarily need to. This is a much more solid resonance structure than the other one. All right, dang. So let's go ahead and take a look at these right quick. These, you can turn them in Monday if you want, but that you can also turn them in, you can also wait and turn them in after Thanksgiving. So either Monday. I'll take them either Monday. But here's what those look like. And these are kind of fun, I think. They're much more fun than those Lewis structure ones. I don't mind Lewis structures, I just don't like those questions. All right. Looks like this. And again, I don't really have any hints. I'm just kind of showing you what they look like. So 17 says assign a formal charge to each atom. You can do that, just like we did. Okay. I guess one thing to think about is, you know, A and B for 17 are both polyatomic ions. That doesn't change how you approach it. It does change that the sum of the formal charges should be equal to the charge of the overall polyatomic ion. Let's see, for C, I bet you guys would buy this. I'll go ahead and expand that out. A lot of times in chemistry, that's actually called a methyl group, the CH3. They just kind of, I think, get lazy. So, not really. But that methyl group really looks like this. Okay, so basically what you're looking at, and that central carbon atom, okay, has another hydrogen. Oops. Does that work? Oh, yeah, I suppose. I know it looks weird. You're like, oh my gosh, carbons usually reach out 4 times. But check this out. It's not a neutral molecule. That is weird to me. But they're all single bonds, so let's go with that. Down here, assign formal charges. I think you should be fine with that. The next page. Through appropriate Lewis structures, show that resonance is involved in the nitrite ion. So, of course, nitrite is NO2 minus 1. Okay, nitrate is NO3 minus 1. So go ahead, draw the Lewis structure. And I should say Lewis structures. I think there might be 3. There's either 2 or 3 structures, but I know there's more than 1. Okay, so you'll need more than 1 there. More than 1 structure. For the 48, which of these require a pair of structures actually to adequately describe them? To me, you have to draw the Lewis structures of all of those, I think. Unless you just pick the one that you know has a resonance structure and at least show the resonance structures for that one. So you have a couple of options. Either draw them all, or at least draw the one that has a pair of resonance structures. All right. That's all I got. So we'll go back on Monday and pick up ionization energy and electron affinity.
I just had a question. With the nomenclature, did we get a big handout that had all the